In the first part of chapter 4, we have defined a vector space and the concept of linear independence. In the second part of chapter 4, which is covered in this video, we'll start by defining a span and a basis. So let V be a vector space over some field f, and we consider a finite or infinite set of vectors in this vector space, and the span of these vectors is defined as the set of all possible linear combinations of these vectors, and it's denoted span of this set of vectors, and what it represents is the set of all linear combinations of the vectors xk. So every vector that we can reach by multiplying each of the vectors with a scalar alpha k and then summing up over all of these vectors, such that these alpha k's are scalars. Definition 4.8 defines what's called a Hamel basis, or simply a basis, and such a basis is a finite or infinite set of vectors that we denote with B. So these are the vectors of the basis if they satisfy the following conditions. First, the set B must be linearly independent, and second, the set B must span the entire vector space V. To illustrate this definition of a basis, let's look at a quick example. The following sets of vectors are bases for R2. The most well-known basis certainly consists of the two vectors shown in blue here, where B1 points in the direction of x1 and B2 points in the direction of x2, and that basis is known as the Euclidean basis. However, any rotation of the Euclidean basis, like the one shown in red here, B1' and B2', is also a basis for the vector space, because we can write every vector in the plane as a linear combination of B1' and B2', and also B1' and B2' are linearly independent. So in this case, B1' and B2' are some other orthonormal basis. However, definition 4.8 does not require for basis vectors to be orthogonal or to have length 1. So for instance, these green vectors B1' and B2' also represent a basis for the vector space R2. So we see that basis vectors do not have to be orthogonal or to be of length 1. In fact, if you think about it, we have not even defined any angles or lengths on our abstract vector spaces. So for instance, we don't know what's the angle between two sequences or two functions, or what's the length of a function. As a second conclusion, we see that obviously bases are not unique, and there may be infinitely many of them for a vector space like R2. Now let's also look some sets that are not bases for R2. And first we consider this vector B1', and obviously B1'' is not a basis for R2 because the span of this single vector does not equal to R2. In fact, the span of the single vector is just this line in R2, but we cannot realize any vector that's perpendicular to this line, for example. Another set of vectors that's not a basis for R2 are B1', B2', and B3'. And the reason is simply that this set is not linearly independent, which you can see from a non-trivial linear combination of 1 times B1' minus 1 times B3' is equal to the 0 vector. From seeing these examples, one may come to suspect that every basis for R2 must have the cardinality 2. What does the expression cardinality mean? Cardinality of a set refers to the number of elements in this set. So in this case, we may suspect that every basis for R2 must contain exactly 2 vectors, like in these 3 examples. And when it contains only 1 or more than 2 vectors, then it seems like this cannot be a basis for R2. Based on this example, one may ask the following natural questions. What is the maximum possible number of linearly independent vectors in a vector space? In particular, if we're dealing with abstract vector spaces, where this answer is not so clear. And the second natural question is, do all bases of a vector space always have the same cardinality? And the results on the next few slides will provide the answers to these questions. For the following results, we will actually restrict our attention to bases that are finite. So the set B consists only of finitely many vectors. Nonetheless, the presented results and arguments do carry over with only very little additional effort to also the infinite case, which is actually a part of the field of functional analysis. However, for simplicity of the presentation, as just mentioned, we restrict ourselves to the case of finite bases. And the first result that we consider is lemma 4.9, which says that a set B consisting of n vectors in a vector space is a basis for this vector space if and only if every vector x in the vector space can be uniquely expressed as a finite linear combination of vectors in B. We will not provide a proof of lemma 4.9 here because it's part of exercise sheet 3. Instead, we continue with Theorem 4.10, which builds on lemma 4.9. And the theorem states that for a set B of n vectors in a vector space, the following statements are equivalent. A, B is a basis for the vector space V. B is a maximal set of linearly independent vectors in V. And C, B is a minimal span of V. Before we proceed to the proof, let's first make sure that we properly understand the statement of the theorem. We understand very well what it means for B to be a basis of the vector space V, but one may ask what it means for B to be a maximal set of linear independent vectors in V, and maximal in the context of sets refers to set inclusion. So B is saying there does not exist a strict superset of B, which contains only vectors that are also linearly independent. And this is also the way the word minimal should be understood in statement C. So minimal also is meant in the sense of set inclusion. So statement C is saying there does not exist a strict subset of B such that the span of the subset is equal to the entire vector space V. In summary, Theorem 4.10 really provides 3 different characterizations of a basis. The first one is the one that we use to define a basis, namely that a basis is a set of linearly independent vectors that span the entire vector space V. The second characterization is that B is a maximal set of linearly independent vectors in V. And the third characterization is that B is a minimal span of the vector space V. Now let's look at the proof of Theorem 4.10. And to prove the equivalence of the 3 statements, we actually prove 3 things. First, A implies B, then B implies C, and finally C implies A. Let's start with the proof that A implies B. By the assumption of A, the set B is a basis for V, and so according to definition 4.8 of a basis, this means that B is linearly independent and the span of B equals to V. The span of B being equal to V implies that any vector V in V can be expressed as a linear combination of vectors in B according to definition 4.7. Therefore, if we consider the set B together with any other vector V in the vector space, the combined set must be linearly dependent, and hence we can conclude that the set B is a maximal set of linearly independent vectors. Next, we prove the statement that B implies C. So this time it's given that B is a maximal set of linearly independent vectors in V. Now we let the set B bar be the subset of B, where an arbitrary vector B in B has been removed. In short, we write B bar is defined as B without an arbitrary element B. Since by assumption B is linearly independent, the vector B cannot be expressed as a linear combination of elements in B bar, or written differently, B is not in the span of B bar. Therefore, it follows that span of B bar is not equal to the entire vector space V. Since apparently no element B of the set B can be removed, such that the span of the remaining set B bar still equals to the entire vector space V, it follows that B must be a minimal set whose span is equal to V. For the third and last part of C implies A, what's given is that B is a minimal set with span B equal to the entire vector space V, and what needs to be shown according to definition 4.8 are two things. First, that span B is equal to V, so that's given. And second, we have to show that B is linearly independent. So for the sake of a contradiction, assume that B is linearly dependent. This means that there exist scalars alpha 1, alpha 2 to alpha n in the field such that the sum of all k from 1 to n of alpha k bk is equal to 0, where at least one of the scalars alpha j is non-zero. Now, subtracting the term alpha j bj on both sides of the equation and dividing by alpha j, which we can do because alpha j is non-zero, we obtain the following expression for bj, namely it's given by a sum over all indices k equal 1 to n except k equal to j of these terms. According to this equation, apparently bj is in the span of the set B without the vector bj. This implies that the span of B is equal to the span of B without the vector bj, but this contradicts the assumption that B is a minimal set whose span is equal to V. Before getting to an answer to our questions in the next theorem, we need a preparatory lemma, and that's lemma 4.11, which is also known as the Steinitz replacement lemma. The lemma assumes that we have two sets of vectors in a vector space V. The first set is a set of m vectors x, which are linearly independent, and the second set is a set of n vectors y, which are such that these vectors span the entire vector space V. The statement of the lemma is that there exists an integer p less than or equal to n and a reordering of the vectors y such that the combined set x1 to xm, so all of the vectors x1 to xm, and a selection of the vectors y1 through yn, so y1 to yp, forms a basis for the vector space V. Now let's prove the Steinitz replacement lemma. It's given that the set of vectors x1 through xm is linearly independent. Since the set of vectors y1 through yn is finite, there also exist finitely many possible subsets y of this finite set. So we can try to add all of these subsets y, one after the other, to the set of vectors x1 through xm, and then look at the cardinality of this set. And now we maximize this cardinality under the condition that this set of vectors has to be linearly independent. To say this again, in other words, we try all possible subsets of the set y1 through yn in combination with the set of vectors x1 through xm, and we only keep those which are a set of linearly independent vectors, and of all of those which form a linearly independent set with x1 through xm, we keep one of the y's that maximizes the cardinality of this set. We call the result of this maximization P, and a subset y that achieves this maximum, we call it y star. Without any loss of generality, we may assume that the set y star consists of the first p elements of the set of vectors y1 through yn, and that's because we could always reorder the vectors in that set. It follows that any of the other vectors that are in y but not in y star, so the vectors yp plus 1 through yn, must be contained in the span of the set of vectors x1 through xm combined with the vectors in y star. And that's because otherwise y star would not be maximal. So suppose one of these vectors was not in the span, then we could add this vector to the set and achieve a subset y that is larger than our subset y star. And since these vectors are in the span of this set of vectors anyways, it doesn't change the span if we add these vectors to this set. So we get that the span of these vectors is the same as the span of the vectors where we have now added the vectors yp plus 1 through yn. Now notice that the span of these vectors must be equal to the entire vector space V, and that's because the span of these vectors here is already equal to V by assumption. So to summarize, we have proved that this set is a maximal set of linearly independent vectors in V, and that's by construction. And we have also shown that this set spans V. So by Theorem 410, it follows that this set is a basis. With the Steinitz replacement lemma in place, we can finally proceed to our result of interest, which is Theorem 4.12. And it states the following: let V over the field F be a vector space. Then, first of all bases for V have the same cardinality, which is called the dimension of V and denoted by dim V. And second, B, any linearly independent set of cardinality dim V is a basis for this vector space. So essentially, everything is exactly as we suspected from our little R2 example. Let's look at the proof of Theorem 4.12. First of the statement A. So let A, consisting of the vectors a1 through am, and B, consisting of the vectors b1 through bn, be any two bases for the vector space V. Without loss of generality, we may assume that m is greater than or equal to n. Otherwise, we could just swap the two sets. Recall that by its very definition, any basis is a set of vectors that's linearly independent and spans the entire vector space V. Now, since the vectors a1 through am are linearly independent, also the vectors a2 through am are linearly independent. Now we can invoke the Steinitz replacement lemma because we have a set a1 through am of linearly independent vectors and another set of b1 through bn of vectors that span V. Therefore, there exists a number p1 greater than or equal to 1 and a reordering of the vectors in B such that a2 through am combined with b1 through bp1 is again a basis for V. And now we can do the same thing again. Since this set is a basis for V, this means that the vectors inside this set must be linearly independent. So if we remove one of them, in this case a2, the remaining set will also be linearly independent. And we can invoke the Steinitz replacement lemma again, which tells us that there exists a number p2 greater than or equal to 2 and a reordering of the vectors in B such that the set a3 through am together with b1 through bp2 is a basis for V. So we continue in the same manner until we hit a limit. The question is, what will this limit be? In each step, we're removing one vector A and we're adding at least one vector B. And by assumption, we have fewer vectors B than we have vectors A. And we're adding possibly more than one vector B in each step. So therefore, the limit we hit will be that we run out of vectors in the set B. And that will happen after at most n steps because we have exactly n vectors in the set B. Hence, after some q less than or equal to n steps, we are left with the set aq plus 1, aq plus 2 through am and b1, b2 through bn as a basis for the vector space V. But as we know, b1 through bn is already a basis, and according to Theorem 4.10, we know that bases are a minimal span of V, and therefore there cannot be any vectors A left in this set, so Q must be equal to M. With Q equal to M, we have therefore obtained that M less than or equal to N, and together with our assumption that M greater than or equal to N, it follows that M must be the same as N. So we have finished the proof of part A of Theorem 4.12, and part B will actually be on the exercise sheet. So we're done with the proof of Theorem 4.12. Based on the result of Theorem 4.12, that for a given vector space, every basis must have the same cardinality, it makes sense to state definition 4.13, saying that this unique cardinality of all bases of a vector space is called the dimension of the vector space, and it's denoted dim V. Note that bases themselves are not unique, as they are sets of vectors. Only the cardinality of these sets is unique. Three major classes of vector spaces can be distinguished according to the dimension of the vector space. The first class are the finite dimensional vector spaces, which are the ones that we're most familiar with. So R2, R3, R4, Rn, C2, C3, and so on. And this leads to the subject of linear algebra. The second class is where the dimension is actually infinite but countable. This leads us to sequence spaces that we have already seen before, which is the subject of functional analysis. And the third class is where the dimension is also infinite but uncountable, which leads to function spaces, and that's also the subject of functional analysis. For most parts of this course, we will stay inside the class of finite dimensional vector spaces. However, occasionally we will enter the realm of functional analysis and look at sequence spaces and function spaces. In the last part of chapter 4, we will look at the concept of subspaces. A subspace is defined in definition 4.14. So let V be a vector space. Any subset of V is called a subspace of V if S together with the field F is itself again a vector space. In order to get a more intuitive understanding of the concept of a subspace, let's look at some examples in R2. So the set S1 here would be an example of a subspace, and so would be the set S2. On the other hand, if we consider this green subset of R2, which we call S3, then this subset will not be a subspace of R2, and also the subset S4, shown in purple here, is no subspace of R2. If for any of these sets S1 to S4 you're not sure why they represent a subspace or no subspace, then what you need to do is go back to the definition of a vector space and check whether all of the properties are satisfied for this corresponding set. Or, to make matters more simple, you can use the result of Theorem 4.15. The theorem states that if V is a vector space and S is some subset of V, then the subset is a subspace of V if and only if it is closed under scalar multiplication and vector addition. Specifically, closed under scalar multiplication means that for any vector x1 in the subset S, we have that any scalar multiple of x1 is also an element of the subset S, and closed under vector addition means that for any two vectors x1 and x2 in the subset S, we have that their sum x1 plus x2 must also be an element of the subset S. At this point, you should at least mentally check the conditions of Theorem 4.15 for the example subsets S1 through S4 that we have just seen in the previous example. Now to the proof of Theorem 4.15, which is really fairly simple. Sufficiency is trivial because Theorem 4.15 is only asking for a subset of the conditions of S being a vector space. Necessity, on the other hand, is easily checked by simply going through the conditions 1 to 6 of definition 4.2. Note that due to the property of closure under scalar multiplication, the zero of the vector space must clearly be contained in any subspace. Here are some useful facts about subspaces. So let S and T be two subspaces, then their intersection S intersected with T is also a subspace. However, their union, S union with T, is not, in general, a subspace. And if S is a subspace, then its complement, which we write by S with a superscript C, is also not generally a subspace. The last two facts can be illustrated by finding simple counterexamples in R2. By the way, if you see statements like this, it's always a good idea to check the plausibility by making little sketches. And that's exactly what your knowledge about linear algebra in 2 or 3 dimensions is very good for. It can give you a first intuition about whether a statement is true or false, and maybe even lead directly to a counterexample. For the union of two subspaces, already a simple example in R2 provides a counterexample. So take the subspace S1 and S2, then the union of these two sets will not be a subspace because, for instance, it's not closed under vector addition. Also, for the complement of a subspace, we can find a simple counterexample in R2. So take the subspace S3. The complement of S3 is defined as the set of all vectors in R2 which are not in S3. And again, S3 complement is clearly not a subspace of R2 because, for instance, we can find two vectors x and y in S3 complement whose vector addition is not an element of S3 complement anymore because it's an element of S3. However, there's something somewhat similar to the union of two subspaces called the sum of two subspaces, which actually is another subspace. So the sum of two subspaces, S and T, written like this, is defined as the set of all vectors S plus T in the vector space, such that S is an element of the subspace S and T is an element of the subspace T. And this now is again a subspace of the vector space V. Now, there's one final definition in chapter 4, which reads as follows. Let V be a vector space and S and T be two subspaces of V. If the sum of S and T corresponds to the entire vector space V, then S and T are called a decomposition of V. If, moreover, S intersecting with T just consists of the origin of the vector space, then S and T are called a direct sum decomposition of V, and we write it with a plus sign with a circle around it. So this stands for the direct sum decomposition.